So thank you for coming. As Martin said, I'm working on the R core implementation now. My background is computer science. I have been doing originally research in language implementations, garbage collection, and so on, and I ended up contributing to R. And this talk is about the bytecode compiler, which has actually been written by Luke Tierney. It was a big amount of work that he did on his own, and I just helped him a little bit in the last few years. So first, to give you some idea what is actually the bytecode compilers, then I have to start with the AST interpreter, which is the older way of interpreting R language that we have in R, and it is of course still there and will be there together with the bytecode interpreter. So here you can see the convolution example, our favorite example, implemented using nested loops. This implementation is from a book by John Chambers. You can see that we have nested loops, accesses to vector elements, arithmetic operations on scalar values. So I will be showing a lot of code in this presentation, but I'm not expecting you to read every line. Just look at what kind of code that is, what kind of abstractions are used. So just the way I described it is enough to understand the talk. And so what R does to interpret this, well, there is a parser that converts such a program into a parse tree. And on the slide I have shown one path through the parse tree from the root to the referencing, getting one element of a vector, so the jth element of vector y. And so you can see that if you start from the bottom, this is the root, that the interpreter is implemented in C functions. They are isolated, and in isolation they implement individual parts of the parse tree, individual operations. So there is a function doBegin, for instance, that implements the brace, and it will call other functions in this program up to the outer for loop. So it's the do_for call, and then another brace for the outer for loop, and another for the inner for loop, and so on and so on and so on. So we will have these nested calls while this program is running, and each of these functions will be implementing something in relative isolation. That's the AST interpreter, and now the bytecode compiler and bytecode interpreter. So we have again the same parse tree, so you can still see the same path through the program, but we first compile this parse tree into bytecode using bytecode compiler, and you can see part of the bytecode in the blue window. So this is a sequence of instructions. Normally, of course, you don't have to worry. This is just to give you an idea what is going on. And this part of the bytecode I'm showing is again to implement the access to vector y, the chase element. So if you start from the very bottom of the blue window, you can see the add instruction. That's addition, obviously. And the bytecode interpreter is a stack machine, so it has the operands on the stack. So the add instruction will take two values from the stack, it will do a sum and push the result on the stack. And then you can see like how it works. Like so the compiler will take a function at a time in this example and analyze the whole function, do a lot of optimizations, and then generate this bytecode. And then bytecode interpreter will interpret this bytecode. So that's the rough idea. Normally you don't have to do anything to take advantage of this now. If you are a user, you just use packages or you write on your own code, and the just-in-time compiler will kick in at some point and compile the code on the background, and then the bytecode interpreter will interpret the code. So normally you don't have to worry at all. This talk is more about how to write code so that it runs fast with the bytecode interpreter, how to avoid writing code that would run slow, and where to expect speedups over what we have seen previously. Because the bytecode interpreter and compiler have been around for a long time, but now they are on by default. So before you had to turn them on explicitly to get some advantages, but now it affects everyone. So this is again the same convolution example. And this example runs 9 times faster with the bytecode interpreter and compiler on a vector of length 8,000. So it's of course a nice speed up, and this includes already the compilation. Currently it works the way that when you first run this function, it will run at normal speed. If you run this, and the loops will be compiled, right? So anyway, if you have other functions without loop, they will be compiled a second time. But the general idea is that this kind of code will run faster than before. Obviously, this is not the case of every code that you would have in R. So the example on the bottom, the convolv v is a vectorized function, convolution vectorized by John Chambers, again in his book. And you can see this function uses an outer product, and this outer product, it hides the loops in them, right in it. So almost no time is spent interpreting in R. All the time is spent in the outer product, which is implemented in C. It's native code, and this type of code that you have on the bottom, as it spends very little time in R interpretation, the bytecode compiler will not help at all. There will be no performance difference with the bytecode compiler on this function. This function is actually much faster than the convolution above, but it also uses much more memory. So in practice, probably you wouldn't want to use either of them. You would probably use a package that does the convolution. But obviously, in some cases, not with the convolution probably, but with some other cases, you can write vectorized code in R that runs well, solves your problem well, and it's still useful to do that. But there is some code that is not easy to write vectorized, and there the bytecode compiler will help. So I will show some more examples. And so this is, I found a study on GitHub that was trying to compare different programming languages, and they had this code. It was they call it stochastic neoclassical growth model, and this code, the performance critical part of it is here. So you can see again nested loops, operations on scalars, if so branches, break. And this code runs 10 times faster with the AST interpreter than before. It is good to keep in mind that it is still 20 times slower than C, but of course it's better to be 20 times slower than 200 times, right? This is an example from a cran package named please. The example, the performance critical part of the code is shown here again, so you can see again nested loops, accesses to matrix elements, arithmetic operations, and that's about it, right? And here we have 4x speedup with the bytecode compiler. Another example is a cran package misstat, example of the function given here, and again this is just the performance critical part. But the speed up 5x is for the whole example. But just the performance critical part is here. It's again similar type of code, operation on scalars. Here also adding things to lists, logical operations, if statements, relational operations, math operations on scalar values. This is the type of code where the compiler will help. And now let's get to functions where the compiler actually doesn't help. So this example is from cran package color brewer, and there is a function brewer.pal. It's a huge function. I'm just showing part of it. It's a huge function that has these switch statements and enormous number of constants in it. And the compiler currently takes really long to compile this function because it has so many constants. So there are slowdowns because of this compilation. You have to wait for the compilation to happen in the background. The function takes about half a second to compile, but still it's a lot of time, right? This is something that, first of all, I would like to fix so that the compilation of such functions are faster. And second, you can actually fix it yourself if you are a maintainer of the package, for instance, by pre-compiling that package, which I will describe later. Another example of code that doesn't work well with the bytecode compiler, and this code is actually something that is good to avoid, something that I think the compiler cannot handle, and something that should be fixed in the package, right? And so there are a lot of variants of this code. This is just one of them in current package mixtocks, where a lot of code is generated. So you can see that this code has many nested loops, and inside them is this paste operation, right? So they are building strings that contain R code, and then very often they would call parse. They parse this R code and eval on it, right? So they just generate R code on the fly very, very quickly. A lot of code, and then they parse it and evaluate, and then call a few times, usually just 2 times, this compiled function, and throw it away. And so the big overhead here is, of course, compilation. So this code will run 3 times slower with the bytecode compiler than with the AST interpreter. However, I'm sure that if this code was rewritten to just have some closures with if statements and switches, it would be much faster also with the AST interpreter than it is now. So this is an example of code that could use some refactoring. There is one more example of something not to do in general, and not only because of the bytecode compiler. If you have a very hot loop, like in one of the recent packages, don't just call GC explicitly in that loop like it is done here. This program spends 85% of time garbage collecting, but it is actually not doing any useful work. It is just repeatedly tracing the same heap all over again, like just the same live memory, not doing anything useful. And there is a slowdown with the bytecode compiler because the bytecode itself contains some code, and so it's just tracing more of the heap. So just removing this call makes the program run several times faster. There is something we can do on the GC side, improving the GC to be more robust against this, and I would like to do that, but just to mention that it is not really a wise thing to call GC explicitly, unless you need to know how much memory is used, but just not this micro fixing of memory usage. One more example, this is also related to GC, but this is not the problem of the package, it's the problem of the GC itself. Sometimes it can happen that the garbage collector would take different decisions when expanding the heap. So when you don't have enough memory, well, you take more from the system. The garbage collector makes this decision. And when you have the bytecode compiler, it itself allocates some memory and then releases, but keeps some. And it has impact on the heuristics of the garbage collector. So sometimes we are just unlucky, and the garbage collector would end up running in smaller heap than before. And this is something we have to fix in the garbage collector. But it may seem as a slowdown of the bytecode compiler, but it is not. Obviously, if you see some strange thing like this, feel free to actually send me an email and we will have a look. So, so to sum up, well, the compilation helps scalar code a lot. It doesn't come without a cost, obviously. So the compile time itself is the biggest cost. And there is a way to avoid it now. It's pre-compilation. So you can pre-compile a package when you are installing it. If you are a maintainer, you can say in the description file that the package should be compiled. Currently, many packages benefit a lot from pre-compilations, some not, and this is something we are going to fix, and eventually we would like to make the pre-compilation on by default, but it is not the case now. So currently, you may get some speed-ups with pre-compiling packages. If you don't care about performance, just don't care, right? There are some patterns that should be avoided when writing code, and the most important one is not to generate R code unnecessarily. I have never seen a case when a package would generate code and it would make it easier in any way, right? Typically, almost always, it's better to have functions with parameters instead of generating code and parsing it. So that's all from me, and I'm happy for questions if you have any or comments.